He's going to be talking about the Annealed Leap-Point MCMC Sampler for multi-modal posterior distributions. So the floor is yours, Matt.
Thanks very much, Sahani. So yes, this is a new algorithm that I've cooked up with some collaborators at Wollongong, in particular Nick Torn and Gareth Roberts. And this is a type of MCMC that's particularly designed for the case that the distribution has multiple modes. So there's some MCMC proposals for jumping between modes and finding the modes and that type of stuff. And our preprint is available on arXiv, and the link is in the web page for this talk. And that paper's currently in review. So just to set the scene and give a bit of notation, I'll just take you through my version of MCMC. So a typical MCMC algorithm, we have some target or invariant distribution pi, and we have a vector of parameters theta that I'm going to assume are in RD. And so we're going to pick an initial value for those parameters. Then at each iteration, we're going to propose, for example, we might have a multivariate normal random walk proposal. And then we have this Metropolis-Hastings ratio, pi for the proposal versus pi for the old value of the parameters. And then Q gives us our detailed balance of our Markov chain. So then we're going to accept this proposal with probability the minimum of 1 or row. Otherwise, we're going to reject the proposed parameters. So why might you need to use Alps instead of just a standard MCMC algorithm? It's well known, for example, with mixture models, that your posterior distribution for your parameters of the mixture model are going to have multiple modes. An example that I'll talk about in this seminar is the curved exponential family. So usually we work with exponential families and they're nice and well behaved and log concave and unimodal, but the curved exponential family is a type of distributions where we have some constraints on the parameters of our exponential family, and that then gives us more than one mode for the distribution of those parameters. And an example of that in econometrics is something called the seemingly unrelated regression model. And I'll talk about that in more detail in a couple of slides. Multimodality can sometimes come about due to problems with identifiability of our parameters or mismatch between our prior and our posterior. It can also arise in ill-posed inverse problems in engineering. So the SUR model was introduced by Arnold Zellner and is very widely used in economics for panel data. And until very recently, because it is an exponential family, it was assumed that there was only one unique maximum likelihood solution, but it turns out that that's actually not the case. So what we have in an SUR model is we have multiple linear regression equations. And then we stack them on top of each other to form a matrix. So these are our m different y vectors. And for each one of these, we have a design matrix of covariates. So this then is our block diagonal design matrix with all of our covariates in it. Then each model has its own regression coefficients, which are our theta that we're interested in. And we have our errors. So far, this is just multiple linear regression. There's nothing particularly exciting here other than our outcome variable y is multivariate. What gives us the multimodality in theta is that our errors are correlated. So we don't have a diagonal covariance matrix in between our errors of our regression model. Rather, our regression equations are all correlated, or all might be correlated with each other. So we have this m by m variance covariance matrix that gives us our correlations between, or covariances, of course, between these equations. So to simplify this down a bit, we can consider the simple bivariate case where we have two different y variables and two different x variables. So then we only have two regression coefficients, θ1 and θ2. And in this Biometrica paper in 2004, it was demonstrated that the likelihood, even in this simple case with only two parameters, can be multimodal. So this is our profile likelihood for our regression coefficients, θ1 and θ2. And here we can see, in fact, we do have two different local maxima of our log likelihood function. Now, what I'm doing over here is something a bit unusual in that I'm raising our target distribution to a power of 10. What you can see that this does is now the two different modes are very well separated. This is the opposite of what we would normally do in this type of situation. Very often we would use parallel tempering, where what we actually want to do is make these modes spread out more so that it's easier to jump from one mode to the other. But in Alps, we do still use parallel tempering, but our inverse temperature is going to be bigger than 1. So in a sense, we're going colder rather than hotter. So parallel tempering, which is also known as MCMC, is generally the most commonly used algorithm when you have this problem of multimodality. So the idea of parallel tempering is that our temperatures are all between 0 and 1. When our inverse temperature beta is equal to 1, then we just have pi. We just have our original target. But we go hotter and hotter and hotter until the tails of our modes overlap with each other enough that we can get from one mode to the other just using a random walk. We independently initialize each chain in our parallel tempering with a different starting value. And then at each iteration, we consider two different types of proposals. There's a within temperature move where we target pi to the power of one of these betas. And there's also a swap move where we propose to exchange parameter values between neighboring temperatures. So we might either swap to a colder temperature or a hotter temperature. And as we run this algorithm, we're exchanging information between this hot temperature, where our random walk explores really easily and visits all of the modes, and our target temperature. Although we run all of these parallel chains, we only keep the MCMC output at our target temperature, and that then is our posterior distribution for our parameters theta. The problem with this parallel tempering approach is that it can converge exponentially slowly in dimension. So as the dimension increases, the mixing of parallel tempering, so up and down all those different temperatures, gets slower and slower. Conversely, as the dimension increases, the more temperatures you need, and that can increase geometrically in the dimension of theta. So in these two papers by Dawn Woodard and colleagues, she showed that the necessary conditions for torpid mixing of parallel tempering were involving these three different terms. So conductance is the ease with which we can get from one mode to another. Persistence is what's can be sort of informally thought of as the spikiness of the modes. So in order to have good conductance, we want our modes to be very well spread out. Persistence is like the opposite of that. The issue arises when we have one mode that might be very spread out and one or more other modes that are very, very spiky. And they have what's known as a basin of attraction, where if you start an optimization algorithm close to the mode, you should then converge to whatever your nearest local optimum is. The problem with conductance is that if the further away mode has a much bigger basin of attraction, you might end up converging to that mode instead and not actually finding this spiky mode. Overlap, we've talked about before, that's just our ability, the amount of probability mass sitting in between those two modes. An algorithm that gets around this torpid mixing problem is the mode jumping algorithm that was proposed by Tjelmeland and Hegstad. And the idea here is, again, we're going to have two different types of proposals. One proposal is just going to be a random walk within whatever mode we're currently in. The other proposal is this mode jumping proposal. So we're going to, our current parameter value is X. And for our mode jumping proposal, we're going to have still a random walk, but with a very large covariance matrix, because it needs to be a big enough jump that we can basically, in one move, jump from the basin of attraction of this mode into the basin of attraction of some other mode. In their paper, they then used Newton's method to find the nearest local mode to this x plus phi here. So they run an optimization until that converges, which gives them their local optimum. Then they're going to take the negative inverse Hessian at this point and do another multivariate normal proposal, which then is going to give them the proposal y. So we've done one Gaussian move and then an optimization and then another Gaussian move. The last thing we need is to preserve detailed balance. So we need this to be a reversible chain. So now what we're going to do is we're going to jump backwards to y minus phi. We're then going to run Newton's method again to find the nearest local mode to this point, which is not guaranteed to be the mode that we started at. But in this cartoon, let's pretend that we're back in our original mode. So that then gives us our probability of x given y and our probability of y given x. So we have detailed balance. Now, as you can imagine, there are many drawbacks to this type of algorithm. The main one is that first you need to actually find the modes, but because of reversibility, we're actually going to forget any modes that we've already found. So we're not maintaining any kind of list of modes in the distribution. We're just doing a really big random walk proposal and hoping for the best. Due to this Laplace approximation with the negative inverse Hessian, the modes need to be very close to a Gaussian distribution in shape. So we can't have modes that are skewed or heavy-tailed. Otherwise, our acceptance probability for these proposal distribution will be terrible. And the issue is that this Gaussianity gets worse and worse, or less and less, the fit with this normal distribution gets worse and worse as dimension increases. So this still has drawbacks when you have particularly moderate to high dimensional problems. And we've introduced our Alps algorithm to address these deficiencies in these two previous methods for multimodal distributions. So what Alps does is combines the best features of both of those other algorithms. We have a Markov chain whose job it is to explore the target distribution at some hot temperature, which is much smaller than 1. And every now and then, this exploration chain is going to stop and do an optimization to see if it's found a new mode. In other words, if it's landed in the basin of attraction of a mode that it doesn't already know about. There's also an annealing component which uses parallel chains. So this is like our parallel tempering, except instead of using temperatures between 0 and 1, we're going to use cold temperatures. So we're going to actually power up the likelihood to one of these powers. The reason that we're doing that is by powering up the likelihood, we're going to get closer to a multivariate normal distribution. So those problems of skewness and heavy tails disappear as we get larger and larger powers of pi. There's also some additional tricks that we use that are a bit beyond the scope of this talk, quantile tempering and Hessian adjusted tempering that improve the acceptance probabilities of swap moves between these temperatures. Then at the coldest temperature, we're much closer to a Gaussian distribution, which means then we can use that mode jumping algorithm with much better acceptance probability than if we tried to do that at the target temperature. So to go back to that two-dimensional, seemingly unrelated regression example, in this 2004 paper, the authors showed an example data set where they had 8 observations with 2 regression equations, and each equation only had 1 coefficient. So we've just got theta1 and theta2. And these are the 2 modes that I showed on that earlier slide. So this is the 2 values of theta1 and the 2 values of theta2 that give our 2 different local maxima. And the log likelihoods at those maxima are different to each other. So unlike the case that we have in mixture distributions, where the other modes are just copies rearranged with the parameters rearranged, these are 2 different modes with 2 very different regression parameters. And then in between those, we have this saddle point. And the difficulty with just a random walk is that we can't get through this saddle point to visit the other mode. So if we start our random walk in one mode, it takes a lot of iterations before we visit the other mode. And then we're going to be stuck over in that other mode for a lot of iterations before we get back again. There's an R package for fitting this SUR model using maximum likelihood. And after 38 iterations, this algorithm converges to this mode, but this is the suboptimal local mode M1, not actually the maximum likelihood estimate, which is M2. So we found the wrong mode using this simple deterministic algorithm that's most commonly used for this SUR model. With our Alps algorithm, we use 3 different temperatures, including the target temperature, plus a hot state of beta equals 1/2. In other words, taking the square root of the likelihood. And although we're running 4 parallel chains here, it only took 2.6 seconds to do 10,000 iterations of our Alps algorithm. We still, in our R package, we need to tune the proposal distributions for the within temperature moves. And we also have these position dependent moves. They still need to be tuned manually, but in our paper, we have theory for theoretical justifications for how many temperatures you need, how cold you need to go, as well as how hot you need to go in order for Alps to work well. So the R package still needs a bit of work for it to be usable by a general audience. But basically the idea here is we have to set up our proposal distributions. We set up our temperature schedule that I showed on the previous slide, and our hottest temperature is just 1 over the dimension. Here the dimension is 2. And then we run our Alps algorithm. And so our mode hunting hot state chain takes 236 iterations to find the second mode. And what we can see here is once we've found that second mode, then we mix much better. So here, until that point, we've basically got the torpid mixing that you would see using a normal random walk or even using parallel tempering, but we get much better mixing between our two modes once Alps has actually found the location of that other mode. The second example is more of a mixture model type of example, but this is not a symmetric mixture. It's an example from spectroscopy. So this black line is a spectrum that we might have in chemistry. And one of these peaks we know should have a shape like a Gaussian distribution. The other peak is what's called a Lorentzian, which is more like a Laplace distribution or a T distribution with 0 degrees of freedom. And then on top of that, we have our additive Gaussian noise. Like the previous example, we have two different modes. So we can swap, due to lack of identifiability of this model, our Gaussian peak and our Lorentzian peak can swap identities with each other. We're now in 6 dimensions here. M2 is very close to the true parameter values that we use to generate this synthetic data. Whereas in M1, our peaks have swapped around. Depending on where we initialize our maximum likelihood algorithm, it's either going to converge to M1 or M2, but once it's done that, the algorithm will finish. So it's not going to find the other mode. Of course, the more peaks there are in our spectrum, the more modes we're going to have in our likelihood. So this is just a simple example in 6 dimensions, but each peak has 3 parameters. And so the more peaks we have, the higher the dimension is going to get. This then is our fitted model. The curve in aqua is the true parameter values, so that's mode 1. Whereas the red dashed line gives us our mode 2. And the only place where that difference is really apparent is down here in the tail of the peak. We can see that if this is a Lorentzian, it's going to have much heavier tails than if this peak is a Gaussian. So that's what leads to that multimodality in this model. In 6 dimensions, we're going to have 6 temperatures, and our coldest temperature is going to be roughly 6. And then we have a hot state of 0.01. Inverse temperature. We're going to attempt mode jumping at these 3 coldest temperatures, 1.8, 3.2, and 5.8. It took 135 seconds for our R package to perform 200,000 iterations in total. We discard the first 20,000 iterations as burn-in because that's when we haven't actually found the other mode yet. This is our exploration component, finding the first mode and then the second mode. So that took about 4.7 thousand iterations. And then this gives our output of our package that gives us our acceptance rate for our jump proposals, which are all above 90%, as well as our acceptance rates for our within temperature random walks, and our acceptance rates for our swaps in between temperatures, and our acceptance rate for our hot state mode finder. The third example I'm going to look at is another SUR model, but in this case, instead of doing a simulation study, this is a real data example that's very often used in textbooks. The data was originally published in the PhD thesis of Grunfeld in 1958, but it's very commonly used. The SUR model is very commonly demonstrated using this data. I'm going to use 15 years of data, and we have 3 covariates in our model. So we have an intercept term. We also have the market value of the firm and the capital stock of the firm for each year. And then we have 5 regression equations for 5 different manufacturing firms. So using that R package system fit, it takes 52 iterations to converge, and it gives us one of the modes in our distribution. Using Alps, we have 9 different temperature levels plus the hot state. And this is because our parameters, our regression coefficients, we've got 5 firms with 3 regression coefficients for each firm. So we have a 15-dimensional problem now. We needed to add some additional features into Alps, in particular, truncating the Hessian adjustment to avoid problems with machine precision when we've got pi to the power of 32 in particular. We were running into some floating point overflow. In this case, it takes 31 minutes to perform 200,000 iterations of Alps for this 15 dimensions. And Alps actually found 3 different modes. And these are the log likelihoods of those 3 modes. The first mode it found corresponds to the same values of our regression coefficients that we found using Zöllner's iterative generalized least squares algorithm. The third mode here has negligible probability mass. So not only is this third mode one of those extremely spiky modes, but actually it has very little volume. So we don't, even though we have this mode jumping algorithm, we never really jump over to that third mode, even after 200,000 iterations, because there's just very little probability mass in that third mode. This is our mode finder, and we took only 155 iterations to find all 3 of these modes. And then this is what the mixing looks like at our target temperature, pi to the power of 1, as well as our coldest temperature, pi to the power of 32. So here you can see in this burn-in period, we had the torpid mixing between these 2 modes. and then much more rapid mixing once the mode jumping proposals actually have kicked in. So in conclusion, I've demonstrated a couple of practical uses of this Alps algorithm for real-world data. So for curve fitting in chemistry, as well as for this SUR model in econometrics. And in both cases, we know that these models are multimodal, but the cause of that multimodality is different for these two models. We do have an R package that we are working on, just trying to set up all of the defaults for all of the parameters of the MCMC, but that we're planning to release that as open source. And future work that we're looking at is using this multimodal algorithm for trans-dimensional MCMC, things like reversible jump. Also for intractable likelihoods, for example, when we need to have a pseudo-marginal step to actually estimate the log likelihood for each parameter values. But there are lots of examples of intractable likelihoods that are multimodal. And the third application we're looking at is using this Alps algorithm for inverse problems where, say, the likelihood involves the solution to some system of differential equations. And these are the main references, including this first one is to our preprint. Thanks, everyone. I'm happy to take questions.
Are there any questions?
Hey, Matt.
Hey.
Thanks, that was very nice. It's good to see that you can work with multimodality. Maybe it's a bit of a silly question, but at the beginning you were saying that to pick up the two modes, you had to do a jump that is kind of like big enough so you go away from kind of the attraction of that jump.
Yeah, to find the other mode, yeah.
And so every time it proposes always a long jump, or it's like it does a long one and then it stays a bit around that mode and then...
So there's a difference between what we do in Alps and what they do in this algorithm here. So in this algorithm, they're trying to, the purpose of this jump is not only to propose to move to the other mode, but you have to actually find the mode as well. Whereas we've actually split that up into two different chains. So in Alps, what we do is we remember all of the modes we've already found. So in our mode jumping proposal, we just look at our list of modes that we know about and pick one of the other modes that we're not currently in and propose to jump to that mode.
So you have a list of proposed modes in the first place.
Yeah, so when the optimizer finds a mode, we remember it. So this is, Alps is more like an adaptive MCMC algorithm. It actually learns where the modes are using this exploration chain.
But would that ensure that you get all the modes?
Unfortunately, no.
Yeah.
So the sad news is that multimodality is still a completely unsolved problem in general. So ideally, you would actually run multiple exploration components first, because the thing is, if you don't have multimodality, there's not really any need to use Alps. It basically just is fancier parallel tempering in that case. So you need to know that you have more than one mode in the first place. Because even in the case, for example, of the SUR model, not all SUR models are multimodal. It depends actually on not only the model, but also the data. And so you need to run this exploration chain to actually know whether there's more than one mode. And then ideally, yes, you want to actually find all of the modes or all of the modes that have non-negligible probability mass.
Yeah, okay. Yeah, that makes sense. Thanks, Matt.
Matt, how does this compare? Have you done a comparison to something like SMC?
No.
Because I mean, you've got a single chain, and with SMC, you've got multiple chains. But I mean, even if you did the SMC with these kind of steps, or not, would it improve the SMC or?
So SMC is quite an interesting case because similar to this mode jumping, the problem with SMC is when you resample, there's no guarantee you're not going to forget about a mode that has particles in it. So you might, for example, say you start with your super annealed, your super hot state version of your target, and you draw all your particles from that. And we're hoping in SMC that our proposal at time zero is good enough that we have particles that are in the basins of attraction of all of the modes. The issue, though, is when you get to a resampling point, some of those particles are going to be discarded, and you're not actually guaranteed that you're not going to throw away one of the modes that you found, unless you do. So essentially what you would want to do is, it's not just that proposal, like you could do Alps proposals at the mode jumping at the MCMC step of SMC, but you also want to do something special at the resampling step so that you don't throw away, so that you have at least some particles in every mode.
Robert, did you want to follow up on that?
Yeah. So to follow up on Scott's question, two solutions. The first one is you are using adaptive MCMC, although it shouldn't be called Markov chain. Adaptive is not Markov chain anymore. To actually keep track of things.
Yeah.
So in the same way, you could do easily adaptive SMC to keep track of things, because you've got this sort of diminishing condition that is a bit fake, but basically you stop sampling at some point. You could have a fake one as well, because but you could do diminishing adaptation in the same way for SMC as you do diminishing adaptation for MCMC, to have a look at it.
Yep.
The other point is that if you reach a mode and you think you're at a mode, you sample around the mode and you build that into your proposal. So now you might have, you discover a mode So now you might have a mixture proposal, one at the mode and one exploring with a random walk. Once you discover a second mode, you've got a mixture of three. Your random walk plus mode 1 plus mode 2.
Yep.
With actually MC or SMC the same way. So I second Scott on that. I second Scott and raise him too. Now I second Scott on that because I think that it might be even more effective than what you're doing now.
Yep. Yeah. Yeah.
And now what?
It wasn't on my list of current or future work, but definitely thinking about how to combine this with SMC is certainly very interesting.
Well, diminishing adaptation stuff that you're using, right? You're using this sort of Gareth Roberts, Jeff Rosenthal diminishing adaptation stuff.
Exactly.
That just says that you stop adapting after a while, and therefore you've got a proper MCMC.
Yep.
But in the same way, you do the diminishing adaptation stuff with SMC. And so at some stage you're not adapting anymore, and on that mode, but presumably on others you are. But anyway, all right. So that's all from me.
Yeah. So I think the argument in the paper around diminishing adaptation is we assume that eventually we're going to find all of the modes, which is a very big assumption, I know, but
no, it's only a little assumption, but it's got big implications.
Yep. Yeah. Yeah. So that's why we're throwing away all of the samples until we've actually found all of the modes.
Yeah.
Essentially, we're just doing a very, very long burn-in until we found all of our modes in this MCMC case.
Yeah. How long is the burn-in? Very long, yeah. Anyway.
It can be. I think in the example 2, it took like 5,000 iterations to find, it took this many iterations to find that mode, to find that last mode. And then at that point, you're not really adapting anymore because you've found all of your modes. So then you can mode jump between them. But potentially, there's no real way of knowing how long it'll take to find the modes, or there's also no guarantee you've found them all. All that we really have is kind of a heuristic, which is in this real data example, where our third mode basically didn't have any mass. We kind of assume, well, if we've explored well enough to find this one, there's probably not any more that have more mass than the ones we've already found, which there's not really any theoretical justification for that. You could get unlucky and just find all of your spiky modes first.
Thank you.
Great, thanks, Robert. And Scott, that was really, really useful. And
that's my warm-up question, and that was the easy one. So my harder question is, so when you're doing the transitions between the distributions, and how do you set your beta distributions in general? But just looking towards your pseudo-marginal stuff, controlling the acceptance rate is quite important in pseudo-marginal, less so than in regular MCMC, because you're going to get stuck in another mode but it'd be a different mode that you can get stuck in if you sort of get these the temperatures wrong.
Yep.
So how are you doing that, either in this setting, or how are you planning on doing that in the pseudo-marginal setting?
Yeah, I mean, I don't know that there's anything special about the proof for the number of temperatures that wouldn't also apply to, well, yeah, so if you're in a pseudo-marginal setting where the likelihood exists, it's just that it's an intractable integral, then I think the theory will still apply for how many temperature levels you need. The other thing is that there's probably a way to check if you've gone cold enough. But in the pseudo-marginal setting, we don't know yet whether, like, sort of the way that we tune this, whether that's actually going to still work for a pseudo-marginal, we don't know. Yeah. I think the argument would still work.
So is the setup like in the regular annealing, where you're doing it hot annealing? There are some, in quotes, optimal acceptance rates to transition between distributions, so you can actually figure out, okay, neighboring temperatures need an acceptance rate of X, and then you can figure out what those temperatures are to achieve that. You can do it adaptively if you want, or various boring ways of doing that. So
Yeah.
is it something like that?
Yes.
And if it is, then I think you're going to have to think about it when you do the intractable likelihood version.
If we're using acceptance rates. Now, these things, the way that we do the temperatures and the coldest temperature and also the hottest temperature don't depend on the acceptance rate. But of course, then we do sort of play around with things based on, see if I can find the slide, based on the acceptance rates that we get. So these are the swap rates. These are the ones for the parallel tempering. And so say that our swap rates were like 0.01 or something like that. Then we play around with adding more temperatures. Because I think in this 15-dimensional case, what I've done is I've added more temperatures closer to 1 to actually get it to jump from the target temperature to the next coldest state. Tends to be the most difficult one.
Yeah, this was the first. This is sort of the problem that people had when these sort of models first came out, right? And they were trying to look at all these different temperature schedules.
Yep.
But things like SMC. It's not what we're talking about here, but you can say, okay, I will go as far as I can in the next temperature jump to achieve some criteria, right?
Yep.
And you can do it adaptively.
Yes.
So other opportunities like that.
So we don't, there are ways to pick these adaptively in parallel tempering. We don't, we fix them at the start. And it does raise a very good point that the way that they do it in parallel tempering is using the acceptance rate, which then in pseudo-marginal, there's other things that can affect your acceptance rate, like if you're doing particle MCMC, how many particles you're using can change your acceptance rate completely independently of anything you're doing on the proposal side of things. You can just have very noisy estimates of your log likelihood. And so your acceptance rate can still be terrible, even if your temperatures and your proposal and everything else is perfectly fine. Yeah, that's a good point.
So you're walking around the space with a random walk, are you?
Yeah, so we have multiple, so each one of these temperatures is a parallel chain.
Yeah.
And so within temperature, we have a random walk. And then this hot state is a random walk combined with optimization. So we do a random walk move, and then we do similar to what they're doing, similar to what we're doing here. So we do a random walk proposal, and then we optimize, and then we check if we've seen this mode before.
Okay. Is that an efficient way to go about doing things?
I think it depends on your model. It depends on your target. If you don't know where the modes are, like in a mixture model, if you found one of the modes, you kind of know where the other mode should be, because it's just a rearrangement. You just permute all of your labels, and that gives you another mode. Whereas in the SUR algorithm case, there's not really any shortcut to finding the location of that other mode. And so for sure, this isn't a fantastically efficient way to do it, because you've got to do some kind of Newton or quasi-Newton method to find your local optimum. And then you've got to compare that to your list of modes you've already found. So it's not cheap computationally to do this, that's for sure.
Okay, I'm going to lower my hand now. And
yeah, so the other approach is, instead of doing this as a random walk, and I don't think I've got that paper at the end, there's a paper by Chris Ladzinski and Amelia Pompey and Chris Holmes, where what they do is they actually raise the target to a negative power. So they have like 1 over the target. And what that does is it's a much better way to escape the basin of attraction of the mode that you're already in. And you hope that that then means that you find the other modes quicker, because that first proposal pushes you right outside the basin of attraction. Because here, for example, okay, we were lucky with this random walk that we found the other mode. If we propose out in this direction, we would have spent all the iterations of our quasi-Newton method and still ended up back in the mode that we started with. So that Pompey, Holmes and Ladzinski paper does have a better way of doing the mode finding, I think.
Okay, great. It's a really interesting discussion there. And thanks very much, Matt, for the really nice talk as well. So there are no further questions. I think we can end the talk. And
well, there are many questions. There's just very few answers. But
yeah. Are you coming to the SSA next week, Robert?
Next week?
Yeah, the New South Wales Stats Society.
Why? I wasn't aware, but now you've made me aware. What's happening?
It's just I'm going to be in Sydney next week for dinner.
Oh, okay. Yeah, I'll try. What day is it?
Thursday night.
Okay. Yeah, I can.
It's over at University of Sydney.
Yeah, that's not too far away. And Sahani, haven't met you, but hello.
Hi, Robert.
You're one of the new CIs at there as well, right?
Correct. Yeah.
Correct. All right. So I'm signing off here from Pennington. So see you, everybody.
Okay, see you.
Oh, by the way, Scott, I bought a house in Woollahra 2 years ago, and I just sold it. So we're in Paddington, but I sold it for a good reason. So anyway, see you later, guys.
Bye, everyone.
Oh, Scott, by the way, you got sent something about Ryan. You have to sign off on something, right? I'll contact you by email.